Oh, hi. It's going to be a little longer lecture than usual, a little more conceptual. We're going to talk about Newton's three laws of motion. So we're making a transition from having talked about kinematics. So kinematics is the study of motion without regard to its cause. Study of motion without regard to cause. And now we're moving into what we call dynamics. Dynamics is the study of motion taking into account its cause. So when we did the uniform acceleration equations, we had acceleration. We said when you have an acceleration, the object goes this far in this amount of time, and maybe it goes this fast, but we never said why the acceleration was there. That's kinematics. Now we're moving into dynamics. We're going to address the issue, well, why did it accelerate at all? And we're going to introduce the idea of forces. So Isaac Newton developed three laws of motion. And we've cleverly named them Newton's first law, Newton's second law, and Newton's third law. So first, Newton's first law. Newton's first law, it's kind of long, says an object remains at rest or in uniform motion at constant velocity unless acted upon by a net external force. So an object at rest remains at rest, or an object in motion moves with constant velocity unless acted upon by a net external force. So this was quite an insight. This says if I have some object, say this brick, and it's not a huge insight to say if this brick is just sitting there, say on some table, it's going to just continue sitting there. But it is a considerable insight to say if it's moving at some constant velocity, that it will continue to do so forever unless acted upon by some net external force. Because in our everyday experience, we see things just come to a stop when we set them in motion. But that's because in our everyday experience, there's always some sort of external force, something like friction or air resistance or gravity. And so Newton had the insight to say, hey, if there were no forces, would it just keep moving at constant velocity forever? And indeed it would. Notice these words, net external. In physics, when we say net, that means sum. So when you see net, it means add up the forces. So anytime we say net, it means add up. There'll be other nets and forces. Net momentum will be add up the momenta. External means outside to the object, not forces inside. And force, what do we mean by force? We mean exactly what you think of every day. A force is just a push or pull. So literally, our definition of force for the moment is merely a push or pull. So an external force is an outside force. So if I apply a force to this object from the outside, say I push on it, that's an external force. But the object, the force is inside, holding the molecules together. Those are called internal forces. The internal forces will never cause it to speed up or slow down. They just hold it together. But an external force, a force from the outside, could cause this velocity to change. And changing velocity is an acceleration. He's saying the first law says if you don't have that, the velocity doesn't change. Now, next we're going to look at Newton's, not second law, that's the most complex one, the most that we'll deal with. We're going to look at the third law. So Newton's third law. So I realize I'm going through this fairly fast, but since it's a video, I'm assuming that you can stop it and take notes or think back on it if you need to. Newton's third law is fairly wordy. It's sometimes called the law of action and reaction, but that doesn't really quite capture its full meaning. Newton's third law says if object 1 exerts a force on object 2, then, that was supposed to be the word then, object 2 exerts an equal magnitude but oppositely directed force on object 1. Those are the action and reaction forces, but again, if you just say law of action and reaction, that doesn't capture the whole thing. So if I push on this wall, I'm applying a force to this wall, but the wall is also applying a force to me. That's what keeps me from falling over. Otherwise, I'd fall. So I push on the wall pushes on me. Those forces are equal and opposite. I'm pushing inward, it's pushing outward. So if I have, someone stands on a table, they apply a force down on the table that's equal to their weight. The table has to push up with a force on them. So the force down on the table is one of those forces. Object 1 applying a force on object 2. Object 2, the table, applies a force on object 1. Those are the action and reaction forces. Those are the forces of Newton's law. By the way, this force pressing up, holding the person up, is an example of a normal force. This is called a normal force. A normal force is a perpendicular force that holds something up at an interface. So a normal force is a perpendicular force at an interface that holds something up. That's not a very classy way of saying that. There's probably a more elegant way of saying that. This symbol, by the way, means perpendicular. You can write the word perpendicular in your notes. So it's a perpendicular force at an interface. So this person standing on the table, there's a normal force pushing up, holding that person. It's called a normal force, holding them up. So, but in this context at the moment, we're talking about Newton's third law, force down equals force up. So, so far fairly obvious. Suppose we have a truck heading down the highway and a fly hits the truck. So there'd be a force of fly on truck, force of truck on fly. So you have to imagine the truck hits the fly hits the truck and goes splat. Those forces are equal and opposite. Now see, the effect is not the same. That force acting on the fly has a much bigger effect on the fly than the force on the truck. So I'm not saying the effect is the same, I'm saying the size of the force is the same. So the force of the fly hitting the truck doesn't have much of an impact on the truck. The force of the truck on the fly is enormously detrimental to the fly. But the size of the force is the same, the directions are equal and opposite. That's Newton's third law. Now let's get to Newton's second law. That has sometimes been called the most important law in all of physics. and I'm going to write it in equation form. Newton's second law says if I have some object and I have some net force acting on that object, then that object will accelerate, and in particular, F net, remember net means sum, is the mass of that object times that object's acceleration. That is Newton's second law. It looks harmless enough, but applying it is really amazing. We're going to spend a lot of time applying it. We're going to learn a great deal about applying it. It's this law that helps us learn how to take rockets to the moon, for example. So this is Newton's second law, F net equals ma. Thinking about it in terms of acceleration, if we just divide through, acceleration is F net divided by m. This just says that if I apply a bigger force, I get more acceleration. But if I have a bigger mass, I get less acceleration. Basically, it's harder to accelerate a refrigerator than it is a toaster. That makes perfectly good sense. The harder you push, the more acceleration you get. But notice it's acceleration that you get, not velocity. And that's a huge misconception people have. People think forces cause velocities. That's not true. Forces cause accelerations. You can have constant velocity without a force. An object can be moving with constant velocity in a straight line forever with no force. Forces cause changes in velocity. That's called acceleration. Forces cause accelerations. Now, a word on units. The units on this side have to equal the units on that side for this equation to be true. If F equals ma, then the units of F have to equal the units of ma. So thinking in terms of units, the units of mass are kilogram, the units of acceleration are meters per second squared. So the units of force equal the units of this. I sometimes put brackets on it to indicate units of. It's a little bit of a misnomer. Sometimes people use brackets to indicate dimensions rather than units, but I use it for units. So the units of force are the same as the units for kilogram meters per second squared. By definition, that's actually called a Newton, to honor Sir Isaac Newton, and we give it the symbol uppercase N. So it's a unit of force. In the British system, unit of force is the pound, but in the metric system, the System International, the unit is the Newton. Newton is about the weight of a small apple. So 100 grams, if you're used to thinking of mass in grams, 100 grams would have a weight of about a Newton. So that's our unit of force. Now, I have to do a little aside, an important aside before we use this equation. So an aside to distinguish mass and weight. So let's call this an aside. Let's distinguish mass and weight. Mass has two definitions that agree with each other. Mass is, strictly speaking, resistance to acceleration. The more massive something is, when you push on it, the less it accelerates. That's from F equals ma. So resistance to acceleration is one definition of mass. That's an important definition in relativity. Another definition, which is very loose, but it's helpful, is how much, I'm going to use the word stuff, is there. That's really vague, but by stuff I mean things like protons and neutrons and electrons, fundamental particles of matter. Mass is what we call invariant. It doesn't matter where the object is in the universe, this mass is the same. If I take this marker to the moon, it would have the same mass. If I have it in deep space, it would have the same mass. Because it has the same number of protons and neutrons and electrons, it would have the same mass. It would still resist being accelerated. Even if it was out in space where there was no gravity acting on it, if I pushed on it and accelerated, it would resist that acceleration. It'd still take a force to accelerate it. Now, what is weight? Weight is different. Weight, by definition, a lot of people miss this, so wake up. Weight is the force of gravity on an object. That's supposed to be the word "and" object. So weight is a force. So if I have an object up in space here, like some sort of ball I've thrown up in the air, gravity is pulling down with some force of gravity. That is what we mean by weight. By definition, it's that force of gravity. And it's very easy now that we know Newton's second law to see how much that is. If this is just falling, I would know that F equals ma. That's our new law, Newton's second law. But I know when things just fall, they fall with acceleration g, and g is 9.8. I'm not putting the minus sign on it at the moment because I'm just talking about the size, how big is this acceleration. But if force is mg and force is weight, this means weight is just given by mg. And that's true. Weight is given by mg. That's how you get weight. So if I have an object with a mass of 10 kilograms, its weight is mg, is 10 kilograms times 9.8 meters per second squared is 98 newtons. Further note, mass is a scalar and weight is a vector. Weight actually is a force and force is a vector. Force has a direction. It matters which way you push. Do you push to the right, push to the left, pull up, push up, pull down? Force has a direction. It's a vector. And so weight, being a force, is also a vector. And it always points toward the center of the earth, here on the earth. Now in other parts of the universe it points in different directions, but here on earth it points toward the surface of the earth, toward the center of the earth. So this is a vector, that's a scalar. So, and I need that for some other examples I'm about to do. Now, so that's my aside on the difference in weight and mass, and as a benefit from that, we learned that force of gravity we can get from m times g. So let's now do a quick example of Newton's second law, F equals ma, and then we'll practice it further with your in class. So here's an object. It was supposed to be sitting on that line, so there's an object that's sitting on the ground or a table. This is an example. And I made this have a mass of 18 kilograms. And I pull on this at a 20-degree angle with a force of 56 newtons. I'm going to cover some stuff pretty fast here, but we'll do it again with the in class. And there's also a frictional force acting of 15 newtons. I tend to use little f for friction and big F for some other force. First, I want to know what is the acceleration component AX in the x direction. Well, I know F equals ma. So in the x direction, this would mean Fx equals max. But remember, this is F net. F net means you have to add them all up. So in the x direction, I've got an x component here. That's F cosine 20, because this force has a horizontal component, F cosine 20, and a vertical component, F sine 20. So in the x direction, I've got F cosine 20. This is also in the x direction, but minus little f is max. All I did was add up the forces in the x direction. This force is at an angle, so I have to look at just its x component. We've learned how to take components. That's just F times the cosine of its angle. This one is, if x is that way, this is in the minus x direction, so I put minus F. This equals m times a, where it's just the x component of a. So a sub x is now F cosine 20 minus friction over m. That's 56 newtons cosine 20 minus my 15 newtons over my 18 kilograms. And that is 2.09 meters per second squared. Second part of my example, I want to find the normal force. What do I even mean by that? Remember, normal force is a contact force that's holding something up. So this box has a weight down. Note that with a force. Weight is a vector. I can call it W for weight, but I know it's equal to mg, so I'm just going to call it mg. But there's a force of the table holding it up. I'm going to call that little n. Sometimes I call it big N, sometimes I call it little n. So there's a weight down, a normal force up. If there were no other forces, those would just be equal, and so the normal force up equaled the weight down. But there's this other force here that's also up. So in the y direction, the sum of the forces in the y direction is MAY. But there is no acceleration in the y direction. The box is neither accelerating upward nor crashing through the table. So this is 0. And in the y direction, I've got this force, F sine 20, plus the normal force. Those are pointing up, minus the weight down, equals 0. So N is F sine 20. F sine 20. Nope, it's not. That's actually wrong. N is mg minus F sine 20. I did my algebra wrong there. Minus F sine 20. So mg is my 18 kilograms times 9.8 meters per second squared. Don't put the minus sign in. I already took into account the minus sign when I put it there. Minus 56 newtons times sine of 20 degrees. So the normal force turned out to be 157 newtons. So that's how much force this table has to apply to hold that box up. You say, why would we care? Well, you could be an engineer where this could be a force holding up some important piece of machinery, for example. So we'll see as we go through the semester many applications of this. All right, well, a little longer lecture than usual, so I'll see you soon.